Algebra 1 students, welcome to your 7.2 notes. Today we're going to look at multiplying powers with the same base. In other words, how do you multiply two numbers that have exponents? So let's take a look at this first. The big idea, I've given you a couple little examples to show you. 3 to the 4th times 3 to the 3rd. We know that 3 to the 4th means 3 times 3 times 3 times 3. And we know 3 to the 3rd is 3 times 3 times 3. And if you multiplied these two together, you would see that there are 7 3's. So we call that 3 to the 7th, which comes from doing 3 to the 4 plus 3 power. Same thing if we have negative exponents. You can see what I've done here. I've got 1/3 times 1/3 as 3 to the negative 2. And then 3 to the 5th we could rewrite as 3 times 3 times 3 times 3 times 3, which is 3 to the 3rd, which would come from 3 to the negative 2 plus 5. Alright, the general form, this is what we're really talking about here. If you have a to the m times a to the n, you could rewrite that as a to the m plus n. Just add your exponents. Alright, and again, it's mentioned down here, but the base has to be the same. In other words, you can't do 3 to the 4th times 4 to the 5th and try to simplify that in the same way. It has to be the same base, and that's what we'll deal with and stick with today. So here are a few examples. First, number 1, 7 to the 5th times 7 to the 3rd. That would be 7 to the 5 plus 3 power, which would be 7 to the 8th. Some of you are thinking, this has to get harder, right, Mr. Hale? And really, no, it doesn't. We can complicate it with negatives and things, but that's about it. X to the negative 11 times x to the negative 6, that's the same as x to the negative 11 plus 6, which is x to the negative 5. Now, one thing to keep in mind, we don't really like negative exponents, so when we can get rid of them, we do. And in this case, we can. We're going to write that as 1 over x to the 5th power. Alright, why don't you guys pause the video, do 3 and 4. The next two on your own, they're really similar to 1 and 2. Alright, students, welcome back. You can see my work on both of these. We didn't run into any negative exponents that we had to adjust, so these might have been slightly easier than a problem like number 2, but on 3 you can add the exponents and you get 6 squared, and then on number 4 you get x to the 11th, again just by adding exponents. Let's keep going here. Alright, so we're going to do some multiplication with exponents again, but this time you'll note that we have more than just one base or more than just one term. We have x's and y's on both of these examples. So let's do this. Let's look at this as two separate problems. One of them is x squared times x cubed, and the other one is y times y squared. Now we know x squared times x cubed is x to the 2 plus 3, or just simply x to the 5th power. Here's the one you have to be careful about. When you see a y times a y squared, remember that it's really y to the 1st times y squared, so we would say that's y to the 3rd. That's it. I told you it's not that tough. I wasn't lying to you this time. Alright, so let's take a look at 6. Similar idea. This time though we have some negative exponents. Again, we can handle that. But we're going to basically group the two terms that have the same base. So my x to the negative 2 and my x to the 5, I want to think of those as one problem. And then as a separate problem, I have y to the 3rd times y to the negative 2nd. And this will just simply give me negative 2 plus 5, so that's x to the 3 times y to the 3 minus 2, which is just y to the 1st, or simply y. Alright, let's take a look at these next two, a little bit different type of problem using the same concepts. If you remember back to elementary school, when you first learned basic algebra, you would see problems like 5 plus box equals 8, and then you had to figure out what number would go inside that box to complete the expression, the addition problem. Okay, this is the same idea here. 7 to the 9 times 7 to the box is equal to 7 to the 16th. Now what we know is that means that 9 plus whatever number is going inside that box has to equal 16. That's the way those exponents work. So we know they're in this case, that our number is in fact 7. Okay, it's the same idea on number 8, the only difference being that we have two variables. We run into something interesting though. Notice on the right side of the equation there is no x value. Now how is that possible? Okay, so here we go. X to the 5th times x to the something has to equal, well, why wouldn't it be there? Because it's a 0 there, x to the 0. So that box right there has to be a -5. I'm struggling with notation here. How do I mark that? That one is -5. I'm just going to write it right up here. Okay, then we can deal with the y problem separately. We have y to some unknown power times y to the 1st is equal to y to the 6th. And we know that box, of course, would have to be a 5. So I'm going to put a 5 right there. Those problems aren't super tough, but it's just kind of weird that we're using boxes instead of variables that we're used to. So anyway, a little flashback to the days of elementary school. All right, so here we go. Scientific notation. This is a process that you've seen, or a notation, I should say, that you've seen. We use it frequently when we have really big or really small numbers. It happens a lot in things like, well, earthquakes, for example. Okay, we don't like talking about numbers that have 27 digits or something. So we use scientific notation. So we're going to write these numbers in scientific notation. Remember, for scientific notation, the A term out in front has to be a number between 1 and 10, inclusive of 1, not 10. Now in this case, that number is 4.326. I'm basically putting the decimal after the first integer, the first number in the term. And then I have to start thinking about, well, how far did I move the decimal? Well, that's 3 places right there. There's 6. There are 9, and then there was one more, so that's 10 places. So this is 4.326 times 10 to the 10th power. I don't think I'm teaching you something for the first time here, but if you're really lost on this, ask questions. We can get you taken care of. All right. Now this one's moving the opposite way. This is a small number, but we still move the decimal until we hit that first value besides 0. So it's going to move to right there. We're going to have 4.1 times 10, and then this is moved 1, 2, 3, 4, 5 places, but it's moved in the other direction, so we say it's -5. So 4.1 times 10 to the -5th. The way to think about that, it's negative here, so I would have to move this decimal in between the 4 and the 1. I'd have to move it left 5 places to get that number. Whereas on number 9, I have to move the decimal right 10 places. All right, on our next two examples, we're going to actually work in the opposite direction. Instead of writing the scientific notation, we're going to actually change it to the standard form, the form we're more used to with most of our numbers. So 8.2 times 10 to the 3rd, this +3 means that decimal needs to move right 3 places. So there's 1, 2, and 3. 8,200 is my number. All right, piece of cake, right? Positive, you move right. Negative, like you see on number 12, we would move to the left. Now when you think about it, if I move this decimal 7 places left, I'm going to have a 3, and then the 6 places before that are all going to be zeros. So I'm going to have 0 point, and then I should have 6 zeros here, and then my number 371. I think when you see a number like this one on number 12, you can see the idea of why scientific notation has some value. It's kind of goofy to write the long number out like this when we can write it shorter here. And as you move further along in classes, like in science classes, you'll hear about Avogadro's numbers, 6.02 times 10 to the 23rd. Nobody wants to write those 24 digits out. We use the scientific notation, the shortcut. All right. The last three we're going to look at are all with multiplication of numbers that are in scientific notation. It's really not too complex, but sometimes we have to make little adjustments at the end, so you have to be careful. Again, we're going to think of this as like two separate problems. The first one is 4 times 2, and the second one is with our tens because they're the same base. We're going to have 10 to the third times 10 to the fifth. So this would be 8 times, and we usually use that x with scientific notation. I don't know why. I don't like it, but I do it because that is the accepted practice, so we'll roll with it, and someday I'll get that changed. But for now, we'll use the x. So 8 times 10 to the 8th. All right, so let's look at 14. It's the same kind of deal as 13. The only difference on this one, well, you'll see it in a second actually. So I'm basically at this point just separating the 6 and the 7 I want to multiply together, and then the two base 10 numbers I want to deal with those separately. So I have 42 times 10 to the third. Now that looks great, except if you just look back at our definition of scientific notation, it said that this a value, the number 42 is what we're talking about, has to be between 1 and 10. So I need to do something about the fact that I'm not between 1 and 10. So I need to move that decimal back one place. I need to make that 42 4.2. And here's the way I think about this adjustment. If I make this number smaller, I better make this number bigger. So 42 times 10 to the third is exactly the same as 4.2 times 10 to the fourth. Okay, again, you have to make sure that a value is between 1 and 9. All right, and then our last problem, we're going to treat this the same way as all the others. The a values out in front, 0.3 and 1.4. That would be 0.42, and then 10 to the 8th times 10 to the 5th would be 10 to the 8 plus 5, or 10 to the 13th. That is lovely scientific notation, except one problem. The a value is again not between 1 and 10. It's less than 1, so we're going to fix it. I'm going to move that decimal one place to the right. So if I move it one to the right, again, I'll have that 4.2 number. I don't know why that happened twice in a row, but there it is. 4.2 times 10, and I go through the same thought process I had back here. I just made 0.42 bigger. I made it 4.2. So if I make that number bigger, I have to make this number smaller so that I haven't changed the value of the term. All right, folks, that is that for today's notes. I hope this makes sense to you. But again, if you have any issues or concerns, you have time to ask about it in class. Have a spectacular day.